Welcome. I'm going to give a quick session on a little bit of background about D-Wave and also a bit of a background of what I do at D-Wave and how the different teams fit in the product and the different services we offer. So we'll go for about 30, 40 minutes, and then I'll open up to a few questions, and then we'll have a panel with a few other people from D-Wave around kind of how we got to D-Wave and kind of our career. So maybe first I'll introduce myself. So I'm Axel. I'm a senior technical advisor at D-Wave. So my role is pretty much working with customers on explaining the technology and also finding great use cases for the technology in their business. So I work in conjunction with the sales team, and I'll talk to kind of new prospects about finding good use cases, and then I'll talk to kind of existing customers about finding additional use cases to work with us on, and then I'll also give a bit of kind of technical advising of advice on how to use the technology and how to use the different products. So I think the slide isn't popping up, but here we go. Perfect. So yeah, I've got a couple slides kind of introducing D-Wave and the product. You've obviously probably heard a bit about it at the different keynotes we had yesterday and earlier today. What I start with usually is to talk a bit about the value of quantum, because I came to quantum computing from a background in optimization, not a background in physics. So when I talk about quantum computing, I talk about what it can deliver for you, not about the qubits and the physics of the actual hardware. And so what's interesting with quantum computing is that I think we're heading to a future where we're going to be able to solve problems that we weren't able to solve until now. So you might have heard about the supremacy paper that we've released. I've got another slide about it in a minute. But kind of these problems where we've taken 1 million years to solve classically, and we could solve in 20 minutes, we don't have 1 million years to solve these problems classically, so we're actually solving problems you couldn't do before, and the impact of that, I don't think we can really fathom already. I think on the commercial side, we're not there yet completely. We're getting to the point where we can solve problems that we couldn't really do classically because of over considerations, but on the commercial side, we usually at the moment are solving problems just better or faster than they could do it classically. So normally where we see improvements is either going to be on the time to answer, so pretty much how quickly can you get to the same level of solution quality, the answer quality, so we have the same amount of time we can get to a solution that's closer to optimal, or the answer cost, so just the overall cost of kind of running the computation. So at D-Wave, we focus specifically on quantum annealing, which is a technology that is well suited for optimization problems. There are other applications in kind of the AI ML space, and then we did a bit of material science simulation. But usually when I talk to customers, we'll really focus on optimization because these are the low-hanging fruits. These are the use cases we know we can deliver really well. So a bit about the supremacy paper that we released. I like usually starting most of my kind of commercial presentations with this because it kind of gives you an idea of where we can be at a commercial level probably in a couple of years. So you might have heard Alan talking about that, but pretty much we were able to solve a magnetic material simulation problem in 20 minutes on our latest Advantage 2 prototype, which is available to D-Wave customers on our cloud platform, so you can actually rerun and retest this experiment. And then running that same problem on the Frontier supercomputer, which is, I believe, one of the most powerful supercomputers in the world, would have taken over 1 million years. But I think even more importantly, it would have actually used the world's annual energy consumption to run that computer for that long, which means that it's actually unachievable, right? So we've solved a problem that we couldn't solve classically, and it's a useful problem. So it's a problem that has applications, so in material simulation, but also the type of problem we solved, which is spin glass, has applications in optimization and in AI and machine learning, so we can actually use what we did here for commercial applications down the line. So a little bit about kind of the technology we offer at D-Wave. So you'll have heard potentially some announcements about kind of what's coming on the Advantage side, so that's the actual quantum hardware. At the moment, what we have in production is the Advantage system, which has over 5,000 qubits. We have a couple around the world, so we've got a couple in our head office in Vancouver in Canada. We've got in California, we've got one in Germany that is now a private system where we can do the kind of more advanced experiments on it. So that's kind of the backbone of D-Wave's technology, and we develop and build these quantum computers ourselves. So there's our own technology. D-Wave's been around for 25 years, so we've had plenty of time to kind of run the R&D on that. It's our 5th generation, And then we're going into our 6th generation, which is the Advantage 2 system, which is the one we use for the supremacy paper. And then that is going to come into production later this year. I'll go into a bit more detail in a minute on the Advantage system, but what I want to talk about is really the Leap Cloud platform, because I think what differentiates us at D-Wave from other quantum computing companies is the fact that we make the technology available to commercial customers. And that's mostly thanks to the Leap Cloud platform. So that's multiple reasons here. First of all, it's a cloud platform, meaning that you can access the technology without having to have an on-premise system. So that means that more and more people can actually get access to the technology. It's also a 99.9% uptime now, meaning that we're actually production ready. So we have like quantum service level agreements. We're SOC 2 Type 2 compliant. So that means that the technology and the cloud platform is as reliable as other classical technologies. So the kind of switch over to quantum is a lot less risky, I guess, for an organization. But I think the most important part about the Leap Cloud platform really is that it gives you access to the Advantage system, so the pure QPU, meaning that you do need some fundamental understanding of how the QPU works, of like the kind of quantum mechanics that happen in the system. But it also gives you access to hybrid solvers. And I think that's really where we stand out, because these hybrid solvers really make using quantum computing a lot easier for our end customers. So in a minute, we'll have a panel, and you'll be able to meet Alex Candello, who's here in the room, and who's been working on these hybrid solvers for many years. At the moment, our latest generation is the nonlinear solver. So the benefits of using the hybrid solvers are kind of twofold, because you have both the capacity of running a much larger problem. So today, we're sitting at 5,000 qubits on the QPU, meaning that there is a limit on how big of a problem you can run in one go on the Advantage system. But you can then also run problems that are more natively formulated. So that means that you don't need to go down to the formulation that is exactly compatible with a quantum computer. You can actually mathematically formulate the model in the way you would for a normal business problem. And I think that gives you really the ability to turn most business use cases into a quantum application quite quickly. And to do that, you use the Ocean Python SDK. So the SDK is the tools you'll be able to use to actually turn your mathematical formulation into an object that you can submit to the Leap Cloud platform and to that API endpoint. So we have our documentation available online. It allows you to build both applications directly for the quantum computer, but also for the hybrid solvers. There's also a bunch of tools on there that allow you to kind of easily formulate existing common optimization problems. So we have like generators for like MVRP problems, like multiple vehicle routing problems. We have generators for some like kind of graph optimization problems. So all of that is part of the Ocean SDK. That's open source, and you can actually start using it before you even have access to D-Wave, because we also offer kind of classical benchmarking solvers. So you can build the application, test it on a classical system without needing access to D-Wave. And then once you do get access to D-Wave, you can then submit it and test it on the actual technology. So that means people can actually even start developing application before getting access to the technology. And then the last part, which I'll go into a bit more detail in, is the launch platform, which is pretty much a professional services team. So we're going to have a couple people from the professional services team join me on the panel after as well. And pretty much their role is just taking customers from a business use case idea to a mathematical formulation. So some of our customers will have in-house knowledge on actually turning like a business problem into a math equation and then submitting that into the API. But some of our other customers just don't have the knowledge, don't have the teams. So we come in and we'll like sit down with them, understand the problem, turn that into the mathematical formulation. Usually it'll be more than one. We'll test different formulations for the same problem, test it against the solver, see how we perform against existing situations, like existing solutions, against other classical approaches, and then kind of deliver at the end of usually a 6 to 8 months project, like a working graphical user interface application. If you've had a chance to come and see us at the demo booths, and I think we're still going to run one again at the end of the day, this is the kind of like applications you deliver after like up to 8 months. So yeah, that's a bit about like the actual tech stack. So yeah, a bit more about the actual Advantage system. So I'm going to go into a tiny bit of like technical detail. So again, this is the chip that's actually inside the Advantage system. We have one on display just outside the main conference room. So on that chip is where the 5,000 qubits sit. Now, because we do quantum annealing, we don't have gates per se onto the chip. So the way that works is that the different qubits are connected together Each qubit is connected to 15 other on this specific chimera topology. On the new system, it'll be 20-way connectivity. But the current production one is 15-way. And so that means that you can actually embed an optimization problem on the different qubits. So each individual qubit is going to represent a decision variable. It's a binary decision variable, so 1 or 0, depending on what the decision is going to be. And then as you encode your mathematical problem onto the QPU, you can use the connection between qubits to link the different variables together. So for example, if one is yes, the other one has to be no, that's part of your problem. That can be physically connected to like the different qubits. And then you run the anneal cycle, which is going to allow to get to the optimal or near optimal solution. So there's a part of probability in solving problems on a quantum annealing computer. So what we will usually do is you'll anneal like a couple hundred times, maybe 1,000 times. So you'll run it 1,000 times with the same problem, and then you'll get a statistical distribution of the different solutions that you had across 1,000 times. And then with that, we'll be able to then come to what we believe is the most optimal solution for a specific problem. The system itself is programmed with what we call a Hamiltonian. I'm not going to go into too much detail, but that translates very well to what we call a QUBO, a quadratic unconstrained binary optimization, which is a type of like mathematical formulation for optimization problems that are used classically, but that does perfectly map to the system itself into the pure chip. And so quadratic, so the highest order is quadratic. The reason for that is the qubits are linked two together, not more than that. So that means that a quadratic interaction can be mapped to a link between two qubits. And then unconstrained is because overall, it's really just one big objective we're trying to optimize. So you're trying to get to the lowest energy for that one objective. Now, you can add constraints into that, but it has to be manually added into the formulation. So you're going to have to use what we call Lagrange parameters, which is like a specific penalty parameter for the constraints. It means that if a constraint is violated, then the objective is higher energy. So we don't take that solution into consideration. And then binary variables, because the qubits are binary, and it's an optimization problem. So obviously, like I said, it's not always very straightforward to convert your like mathematical optimization problem into a binary optimization problem, right? In some cases, you might need to use different types of variables. It might be discrete, it might be continuous. Also, you might need more than 5,000 qubits, which kind of represent 5,000 binary variables. So you might be running much bigger problems with kind of more complex formulation, and that's when the hybrid solvers come in. So the hybrid solvers are a combination of kind of classical solving power and quantum solving power. And so we have an entire team at D-Wave that specifically works on developing these hybrid solvers. So you'll submit your problem as one large problem. It can take up to 2 million variables on the latest nonlinear solver. And you can now, since I think earlier this week or last week, submit problems with continuous variables. And then we're going to take that problem and then use our in-house algorithms to decide what's going to be solved classically, what's going to be solved with a quantum computer, and then we're going to put all the solutions back together and then submit as one solution to the overall problem you were submitting with the 2 million variables. So most of our like business applications and kind of like commercial customers will be using the hybrid solver. In my role, I mostly talk about the hybrid solvers. We obviously do work with a lot of kind of academic institutions that are going to be more interested in kind of how they're using the QPU and how to like program the QPU, play with the different parameters. But when we're talking about delivering business value, this is really the kind of product that we're using. And so talking about delivering commercial value, so we are actually the first commercial quantum computing company, meaning that we actually bring value to customers with the technology. So obviously, a lot of quantum computing companies will be working with customers. Usually, it's more of like a proof of the technology, or they're going to try and understand how it could impact their business in 10, 15 years' time. In our case, we're actually delivering value, meaning that you can get an ROI from the technology today. And that's also what allowed us to be the first quantum computing company to have clients in production. So they're using the technology to make business decisions in their day-to-day operations. A little bit about kind of the different clients. I'll go into a bit more details about a couple of use cases. But so we've worked with Vinci, we've worked with MasterCard. You've probably heard about a few of our different clients that we worked with in the last year on stage here at Qubits. Ford Otosan was just announced to have gone to production. So that means that we were running a project with them for, I think it was about 8 months. We took them from like a business problem to a mathematical formulation. That was done by the professional services team that you'll get a chance to meet later. And then they took that problem and turned it into the production application that they're using today that is running on like the back end that actually makes decisions for the day-to-day operations of their factory. So a little bit about these different use cases. So I'll focus on these 3 use cases. All 3 of these use cases are actually in production today, meaning that they're using our quantum system to make decisions on the daily. So in the case of Ford Otosan, I know they will run it about 3 times a day. So that means that they take data from kind of a production line about how things are running, if things are getting delayed, if like a specific kind of machine might be down, if there's a change in the order book for the day, and then they readjust the scheduling of how the different vehicles are going to be assembled across the production line. So they're manufacturing 1,000 vehicles a day. So Ford Otosan is based out of Turkey. They manufacture the kind of transit vans, so the large vans from Ford, for all of Europe. So their throughput is 1,000 vehicles a day, which is pretty large. And then up to now, they were using kind of a classical system that could get to some sort of solution in 30 minutes. But really what's interesting here is it wasn't getting to the optimal solution, and they couldn't actually encode all of the constraints. So we tried to solve a full problem. They just couldn't do it classically. Their like existing system didn't work. We were able to not only do it much faster in 5 minutes, but actually take into account all of the different variables that the problem entails, meaning that we were getting a better solution, not just because the system was running better, but because we were able to take in more data. So like something I like to say about kind of these use cases is running faster isn't just about like, oh, we need to run it faster because we don't have time to run it throughout our process. It's also running with more up-to-date data. So if we look at the Patterson Food Group example, we're able to run their scheduling 80% faster. So they were roughly, I think, taking 48 hours and like 3 full-time employees to decide how they were scheduling their e-commerce delivery drivers, so who's delivering where pretty much. When it comes to like, when we're talking about thousands, if not tens of thousands of employees, it's a very difficult problem to solve. If they can give them roughly 48 hours, we could do it 80% faster. So that, first of all, means that they're saving time and money, but they don't need 3 full-time employees working on this for 48 hours. They're now running it in a few hours. But more importantly, it's that the data they have to be able to run the optimization is a lot more up to date, right? So a couple hours before you have to run the deliveries, you might have way more data on like where you need to go, if a specific van might have broken down, if like a delivery got canceled, if someone didn't show up at work that morning. So you can then reschedule with better data. So you actually get a better solution just by the fact that you're using better data to start your optimization. And then the entity Docomo use case is a pretty interesting one. So in that case, they actually developed the application themselves. So you might have seen they gave a talk yesterday morning about how they got there. So in that case, what we're doing here is that they're optimizing what we call paging signals. So it's the signal that your mobile device will send to the tower, like the cell tower, to detect if it's still connected to the right network, pretty much. Obviously, these signals use a certain amount of bandwidth. So that means that as you're sending these paging signals, you're not using the existing bandwidth to be able to send a message. And so by optimizing how they're sending these paging signals and how they're kind of cutting down the different zones of a network, they were able to increase the network performance by 15%, which pretty much means they were increasing the capacity of the network by 15%. So without any additional hardware installations, they could have 15% higher capacity on their network just by running optimizations. Again, that's something I believe they tried to run classically and never really managed to get there. So we didn't really replace an existing solution. We actually came up with a solution that they didn't even knew could be done on the classical solver. So maybe a little bit more about each of these different use cases. So Patterson Food Group, if you have a chance to come to one of our demo booths, we're actually running a demo for staff scheduling, which is pretty similar to what Patterson Food Group are doing. Obviously, they're doing it at a much wider scale than we are on our demo. And they're also using this fully in production. So the story with them is quite interesting, actually, because we, I think, got in contact with them a few years ago. And then we came up with, I think, what was a good use case to solve for them, which was this employee scheduling for delivery drivers. And then the professional services team at D-Wave worked with them on building the formulation. So we talked about what are your problem constraints. So there's like constraints around like, how many hours a driver can work in a row, like how many days they can work before taking some time off, pretty much what driver can drive in what area. There's also preference based on seniority, so the more senior drivers can have preference in the shifts they want to run rather than more junior drivers. So all these different problems that are formulated in words, we will take that and then we'll turn that into a mathematical formulation. So we'll use a decision variable, which can be binary if you're running directly on the kind of QPU. But in that case, we were able to use the hybrid solver and use non-binary variables, which is a lot simpler to schedule. So you can imagine for each driver, you can use a discrete variable, which will tell you what day they're going to work during the week, for example. And then we were able to then turn that into an application with a professional services team, and then that went into production. And then Passive Food Group came back to us and like, okay, now that we're running this in production for kind of driver scheduling, then can we do this for the actual staff in the stores scheduling? So that was a little bit more of a, like actually it was a much more complex problem because there's a lot more rules around that. I think it's unionized, so there's a lot of rules around the union. So being able to match all of these different requirements and still staff the stores as required is something that is very, very difficult classically. And they had a solution that wasn't really working. So because they'd done the first project with us and used the professional services team, they were able to actually develop that second application completely in-house. So they kind of learned about how they could develop quantum applications, and they were able to develop that in-house and then take it to production on their own, which I think is kind of where we're hoping to get to, right? I think at D-Wave, we're in the business of selling access to the machine. We have a professional services team which is here to enable people to get access to the machine, but if we can teach people how to use it and then build their own applications, this is going to allow us to scale much better. A bit more about NTT Docomo again. So yeah, like we talked about, the use case here is about these paging signals. So in that case as well, they were actually able to develop from the get-go their first use case in-house with like in-house experts from just the information we had available online on how to use our solvers. So what's interesting, like I said, is that we were able to get results to the problems in 40 seconds. And when they were using the kind of general classical solver, they were getting the roughly same quality of result. They was taking 27 hours. So this is the kind of like improvement in runtime that we can expect using our technology these days. Like I said, so in some cases we're running faster, like in Passive Food Group, like NTT Docomo, and in some cases we're just getting a better quality solution. And so yeah, by reducing the paging signals by 15%, that means that they can actually connect more phones to the whole network, meaning they're increasing the network capacity. With another similar use case that we did with the Port of LA, so that one was also a similar one where they were actually able to reduce the capacity of, they were able to increase the capacity of the hardware. So you can use the existing hardware more efficiently, meaning that you're getting an ROI from the fact that you don't need to increase your hardware capacity to be able to allow more customers to be serviced by the system. So yeah. And then a little bit about Ford Otosan. So Ford Otosan, because they're in Europe, they're actually my customers. So I worked with them through like the discovery phase, through the professional services phase, through what we call the pilot production phase, where they kind of tested where they'd gone out of a proof of concept and tested it on the production level problem. And then now they're in production. So kind of like we offer support throughout the production phase and kind of these service level agreements. So specifically for that one, like I said, so it's about the actual assembly line of a factory. So as the different kind of vans come through, they all have different specifications. So it might have different colors. It might have different kind of grade of wheels, of doors, of seats inside the van. So all of these different steps are going to take a different duration on the different stations at the factory. The idea is that if you're running all of the very complex, kind of more high-end vans in one go, then you're taking much longer at each step, so it's slowing down the production. So I think if you saw the keynote from Alex Candelo on yesterday on Monday, you'll have seen that when we run the demo, like one big part is making sure we meet all the constraints. So by the end of the day, all 1,000 vehicles has been assembled, like everything has been done as we should. But another thing that they could add on to it that we weren't able to do classically was let's try and spread the load across the system. So rather than like have a really high load, build all the complex vehicles first, and then like a really low load, build all the simple vehicles next. It's about like managing that and interchanging between high load and low load, so to make sure that there's less delays in the production. But again, there's always unexpected outcomes throughout the day, so that means that if they were running this classically and taking too long, they're not able to reschedule as we go. In our case, by taking just 5 minutes, they're able to actually take existing data on how it ran and how like the delay that might have happened just caused by like a machine coming down or someone taking slightly longer at a certain step, take that into consideration and then rerun that into the optimization and then decide how to adapt the rest of the day. So the last thing I want to cover before opening up to questions is a little bit about the difference in the technology. So I know we talked a little bit about how at D-Wave we do quantum annealing and how that's different to gate models. And it seems to be an error with the slide, but pretty much, like, I think the reason D-Wave is where we are today is because we took that bet a few years ago on focusing, well, more than a few years ago, but on focusing on quantum annealing because we believe that we'd be able to take that to production earlier than something like gate model. And I think what's interesting about quantum annealing is, first of all, we don't run into these error correction problems that we do on gate models, so that allows us to go to production today. But actually, by its nature, because the native formulation for the QPU is this QUBO formulation, which is a pretty common way of formulating an optimization problem, the kind of learning curve for someone to learn how to use a quantum annealer is much lower than someone learning how to use a gate model. So if you've ever had any experience with gate models, you need to understand how you can program the different quantum gates. It gets very complicated. With quantum annealing, actually, most of the work that you do, you don't even have to worry if it's going to run on a quantum system or on a classical system. You're just turning it into a mathematical formulation that you can solve on other classical solvers. Then once you get to the submission part, which is usually just at the end of a project, then there's a couple of parameters you can play with, and then if you're submitting directly to the QPU, then I need to understand a little bit about kind of like the penalty parameters, about like what we call the embedding, which is how you actually embed the different variables and the different qubits, so how you assign a variable from your problem to an actual physical qubit on the chip. But because we're offering hybrid algorithms, now you don't even need to go into that much detail. It's really about getting that mathematical formulation, submitting it to the solver, and then getting a response back. Now, the downside, if you can call it a downside about going the annealing route, is that we're limited to specifically kind of optimization problems and then a couple kind of machine learning applications. So most of the use cases you'll see that we present and that we're doing with customers are usually around optimization. So for example, workforce scheduling, that's what we did at Patterson Food Group. Production scheduling, like what we did with Ford. Like logistics routing, so that's another application that we see quite a lot. Resource optimization, which I think is a bit like a general one, which is like how do you assign different resource to your different business applications, and this is in itself is an optimization problem, and cargo loading as well. There's a bit of a crossover between annealing and gate model, which is around kind of like machine learning. So you'll have heard a couple of announcements that we've made about like results we've had in this space, and that we're actually enabling more and more of these machine learning applications by enabling tools on the Ocean SDK that can help you build these much easily. And then on the gate model, there's applications that we don't believe we could really run efficiently on the annealing, so we'll leave that for gate model, but we believe we'll be about 7 to 15 years away from having that in production, so that's a lot around kind of simulation, so like 3D fluid dynamics and quantum chemistry. So really a big part of my job is going into an organization, and usually they'll probably have a use case for every single one of them on screen, and it's deciding, well, first of all, let's make sure we're choosing something on that side of the screen because we know we can solve it with our platform. And then out of these, how do we select the right one, right? So like, is the formulation suited for the technical like capabilities of the solver? That's probably one of the easiest requirements because I have a good understanding of what works well. If you can explain the problem well to me, then I can tell you, yes, that'll be a good fit or not. And then there's a lot of other different kind of factors to take into consideration here, which is, for example, like, does the problem deliver any value? Like, are we solving something that actually helps your business? Because if not, we're probably not going to get any drive in building that application. Other ones are around, like, is the data available? Like, we've had a couple use cases where, like, it's a great use case, but then when we delve into it, you realize we don't actually have any data to inputs to be able to optimize. Like, things aren't recorded the right way. It's the, like, technology is too ancient and we can't connect with it. So really, a lot of the work is talking to the business, understanding what their requirements are, how the different use cases fit into our technology, and then if it's practically if it's practical enough to set up this application in the business and actually use our technology in production. So yeah, that's what I had for you guys today.